Can you see my mouse that is?
Okay, welcome all. Today we are having the fourth webinar of ITU AI Center, which is the shortened of Istanbul Technical University Artificial Intelligence and Data Science Application and Research Center. Quickly, my name is Berk and I am the director of ITU AI, also a faculty member of our newborn Artificial Intelligence and Data Engineering Department. I am also a vice dean responsible from Research and Development Affairs of Computer and Informatics faculty at ITU. So today we are having a special guest. We are hosting a special guest from far, far away, right? From Boston, from United States. I know it's early morning there, like 9 a.m. Professor Kaushik Chowdhury from Northeastern University. Professor Chowdhury, before I leave the scene to you, I want to give like a short brief introduction of yours, if you allow me, and then I'm going to leave the scene totally to you. Kaushik Chowdhury is a professor in ECE Department, Electric and Computer Engineering Department at Northeastern University. He received his PhD from Georgia Institute of Technology from Georgia Tech in August 2009. Professor Chowdhury is the winner of the US Presidential Early Career Award for Scientists and Engineers. I know it's quite a prestigious one. The DARPA Young Faculty Award, the ONR Director of Research and Early Career Award in 2016, and the NSF Career Award in 2015. He has won multiple Best Paper Awards, including Infocom, Globcom, ICC, DICEPAN. I mean, there are some others that I don't remember right now. And so many awards that he won, so he asked me specifically to shorten it. Anyway, so his research interests include machine learning applied to wireless systems and network robotics. Kaushik, as a long-term collaborator, maybe 15 years, we are really happy to have you today. I know, again, it's really early in the morning, so thank you very much joining us. This subject, like AI and 6G, AI and smart networks, is really popular, really hot, and quite interesting. We are really good to hear your opinion and your talk. You are an expert in this area, so I'm sure you will give lots of motivational vision and research topics related to this subject. So I am stopping myself. I will leave totally the scene to you. Again, welcome, and thank you very much for joining us today, Kaushik.
Thank you very much, Professor Canberk. This is indeed an honor to be here and address this young and growing and very timely institute. I can see great things in the future ahead. So, as Professor Canberk mentioned, I go back a long way, especially in my association with ITU and especially Professor Canberk's research. And so I'm delighted to present a talk today called Intelligent Wireless Networking. And I want to present a vision as to how a specific kind of machine learning applied to wireless in terms of RF fingerprinting will help transform some of the future networking, authentication, header compression, and identification purposes that will become an integral part of future 5G and 6G networks. So with that, let me get started and introduce my lab very briefly. So these are the outstanding, intelligent people who I work with. As they say, right, you surround yourself with people better than you, then you don't have to work at all. So these people really do the work. I'm just here presenting their work today. So with that said, I'll move forward and talk a little bit more about the problem and motivation. And hopefully I should be able to explain to you why this is an important problem to tackle. So let's get started and think about the massive scale of IoT devices that are there today. So the vision is that as you go forward, you will have sensors pervasively deployed all around us. And there'll be a variety of different kinds of sensors to the point where you have to identify that this is really your sensor giving authenticated data versus something else or someone else who has maliciously put a sensor in your vicinity. So verifying data and verifying the source of data is going to be extremely important. In other words, you have to know that this particular device is authenticated, is authorized by you, and not a maliciously placed device. So what scale are we talking about? So we are talking about a market segment of about $1.7 trillion just by the end of this year, right? So we are increasing at an exponential rate at the number of devices that are being connected. So if you extrapolate another 5 more years, you see about more than 200 billion devices. Now, this becomes a problem. If you have this kind of a density in an environment, how do you know that this sensor is truly what it's claiming to be? So you can say, hey, you know what? Every sensor has an ID, or we can use cryptographic methods. But the problem is that if you deploy this on a very wide scale, it may happen that these are small resource constrained sensors, not always possible to run complex cryptographic techniques. And today's software methods are getting more and more sophisticated, where you can easily overtake an operating system on a small device and inject code on it, make it assume a different identity. So we need to come up with a way in which identity is hard-coded and not easily spoofed by software methods. Another thought here is look at the way in which our protocols are designed today. So this is a standard header format of a Wi-Fi 802.11a medium access control header. So in other words, if you're sending a Wi-Fi packet, your packet has this kind of a header where it has a bunch of these control fields. Now, if you look at the amount of fields that are just dedicated to addressing, and if you remove those addressing fields, you find suddenly the header itself has been compressed by 80%. So now it's a very small amount of information that you need to send. So now the question is, if I can find a way through machine learning to identify which device has sent this packet, then I can perhaps even remove these address fields and make a complete addressless packet. Now, yes, it reduces the space in terms of bits, but what does it mean in terms of energy and throughput? So if I go to this next chart on the right-hand side, you see the situation where we have different packet sizes. So look at the 64 packet size. So this is the 64 byte packet size. As you can see that if I do this kind of a compression, then you are able to enhance about 25% the spectrum utilization. In other words, you are reducing useless waste of spectrum by 25%. So that's a big change. And simply because you are transmitting bits which are not containing data. So these are all control fields. They don't contain useful information, data bits. So if you can reduce this through some kind of machine learning where you can identify who has sent this packet, you don't have to include so many address fields. You can save more for data. And similarly, you also save energy. So a similar logic flows there. So this is just the takeaway messages for a simple example: 64 byte short packet, 25% reduction in spectrum utilization, 23% in energy saving. So this is what you will get if you can do this. One last example is as follows. So today's 5G networks are talking about hardware as a service. So what will happen is that you have a bunch of these base stations, and you'll be able to run different network slices on each of them. So that means that in one time, this combination of base stations will have, someone will be Wi-Fi, someone will be running a 5G NR waveform, some others will be running an LTE waveform. So all this is one-time snapshot. It can happen that over time, you will be able to change the waveform, you will be able to change the software stack, and completely change the way in which such a device is working. So in the second figure down, what you see here is that some of these base stations are the same, but what if a malicious entity comes up and captures these two base stations on the right-hand side and still advertises the same base station ID as was advertised previously here? Okay. Now, because no network operator owns all these hardwares end to end, this hardware can be allocated to different operators over time. So you have no way of knowing that if this same ID is broadcast by this base station 4, whether this is really, for example, T-Mobile, which was transmitting earlier, or if it is Kaushik Chowdhury's private base station, which has now assumed the identity of that previous base station, but is now spuriously transmitting data, perhaps even taking your data and saving it in an unauthorized manner. So to overcome this, what if we could add a level of trust into the way in which these networks are designed, where we could identify a base station and say that this is truly that base station that is claiming to be. And to do this, we can use a machine learning architecture and a technique that I will talk today. And I'll show you how you can build trust and ensure that this base station is truly what it is claiming to be. And I'll show you some results based on actual experiments which we have done over the air. One last example is the complex task of detecting UAVs. So unmanned aerial vehicles are being rapidly being produced in the market. They're cheap. You can buy them for a couple of $100s. This is an example of an M600 UAVs produced by the DJI company. Now, this particular model was used for a terror attack on the president of Venezuela sometime back in 2017. Now, this is the same model blown up. Now, you would say that, hey, this is the model. So, if you see this model, as soon as we can recognize this model, if perhaps visually, you'll be able to say that this is an adversarial model and it must be taken out. But the problem here is that, as you can see, if I just show you the rest of the picture, this is nothing other than the same model that is actually used by the US forces to perform counter UAS operations. So this is actually a friendly UAS, which is used to counter the malicious UAVs, which might be violating your airspace. So, but just by looking at it, you can't say that this is friendly or if this is adversarial. So you need another way of finding trust and identifying and authenticating and recognizing a device. So all this brings us to the method that we're going to talk about today. And the method is going to be RF fingerprinting. And I'm going to delve a little bit into wireless topics. So I'll keep this at a high level, but please, happy to answer questions in case something becomes a little bit too tangential. So what is the problem? The problem is as follows. You want to identify a device based on some unique characteristics, a unique signature that is embedded in the device. Now, the way to do this is think of this as a regular wireless transmitter chain. You have your baseband signals, and they're going through a digital to analog converter. There is a mixer, and it goes through a power amplifier, and it goes through the antenna. Okay, so you don't really have to be a wireless expert to really follow this discussion, but just keep in mind that there are a number of processing steps from the point the signal comes in and the point the signal exits the antenna. But within those processes, there is a number of changes and distortions that are added into the signal. So for example, what the plots you see on the top and the bottom two are nothing other than what we call our IQ sample plots. Now, IQ sample plots show you the in phase and the quadrature component of a signal point. So if you just keep at that definition, that is enough for the rest of this talk. So an IQ sample is a representation of the signal in a complex domain, in which case the real part is shown in the I and the complex part is shown in the y-axis. And then these points, each point such will represent a discrete IQ sample. And a number of these IQ samples will produce a symbol, a number of symbols will produce a bit, a number of bits will produce a packet. So it's just just breaking down a large complex packet into its most fundamental atoms. In this case, these are IQ samples. Okay, so that's all you need to follow on this. Now, the fun part here is that as these electronics operate on these signals that are passing through, these IQ samples are distorted. Now, these distortions are shown here. For example, if you look at the plus signs, the plus signs are the signs where you have a distortion from the original reference point, which is the red dot. So in an ideal world, you would expect the red dot nicely arranged in a 4x4 representation. So this is a 16-point representation. So you have a perfect representation if you have only the signals coming at the red points. But the truth is that you're going to get these pluses because you see these distortions, you see the movement that they have shifted. This is because of the hardware of the electronics that is causing harmonic distortion, imbalances, nonlinear amplification, all these things that happen in a hardware systems chain. So now your goal is this. Your goal is to identify a characteristic device from these signatures that are there in these plots. So what you get is just a jumble of these plus points. It's a jumbled piece in which there is an embedded signature. And you have to find out what the device is by learning how much was the distortion of these black pluses from the red dots. And many of these distortions can happen in a superimposed manner. So it's not clear which signature is present in which device. It is not clear where you should even be looking for, but the signature is embedded inside, you know that. So because constructing or identifying deterministic features are difficult in these environments, we have to pursue a technique called as deep learning. And a specific approach in deep learning that we use in this work is we use deep convolutional neural networks to identify a specific device from its shifted IQ sample signatures. So that's what is going to be the objective of this talk. And I'm going to tell you how we're going to do this. So to do this, let's go a little bit further and understand why convolutional neural networks. So this technique has been successful in a variety of tasks, and you can see them in image processing, speech recognition, natural language processing. You use convolutional neural networks in all these places. And the advantages of this is that they are lower dimensional models. They are going to exploit locality, and they're shift and rotation invariant. And I'll talk a little bit more about this very in specific terms as we go through the next slides. But at a high level, this chart on the right-hand side shows you what is a convolutional neural network. So all I'm doing here is that I'm passing a filter. So if you can see this little square out here, this is the filter that I'm moving across this entire feature set, right? And each time I'm moving this across, I'm obtaining a convolutional output, which is smaller than this entire size of this filter. So if you see, this is the process here. You see the filter that is sort of moving left to right and then going one row down and then moving left to right. And so this is the convolutional step that is creating this smaller representation that you see on the top. So this is in general what a convolutional neural network does, and we'll be using this one as we talk about the rest of the methods. Okay, so now let's talk about how are we doing some of this data processing and data pre-processing before we get to the actual network architecture. So, there's a saying that says that if you torture the data enough, it will reveal everything it has to say. So our goal here is to take the data and pre-process it in a way that makes it easy for our network to understand. Now, remember I said that in a wireless network, you're looking at a stream of IQ samples. So think of him as a long vector, as you can see here, a long vector of IQ samples. Now this is coming in, so each sample is coming in over time. So think of it as in time, you are getting one sample and then you are doing something with it. So what we first do is that we take these samples, we group them together in what we call as an example. So when you're given a training or a testing set, you're given an example. An example is nothing other than a group of IQ samples taken together. It's a vector. Now, first, I need to partition this example into smaller pieces, what we call as slices. So here is this thing, right? So device is generating its signals over time. I'm getting an example, which is a stream of IQ samples. I'm going to chop that example into smaller slices, and that slice that you see here. And the same thing is what you see here. I'm slicing the example into slices, and I do so by a sliding window. The window moves forward. As the window moves forward, slices are formed. Okay, so and my input to the neural network architecture is going to be a slice. So the smaller slice is what I'm going to feed into a neural network. Now, for training or testing, I'm interested in the example, not the slice. The slice is what I have created. So once I get the outputs or the output probability vectors for each slice, I'm going to combine them to come up with a unified decision for an example, because that's what I'm ultimately interested in. All right, so let's move forward. And just to say, there are a variety of ways in which you can evaluate the accuracy. Remember that in the output of the neural network at the last layer, what you get is simply a vector of probabilities. The vector of probabilities simply says that so-and-so probability, with so-and-so probability, you say that this incoming slice belongs to device 1. With probability so-and-so, the incoming slice belongs to device 2. So you get a vector of probabilities. So all we do is that we take the sum of probabilities for all the slices of an example to say, and then we simply take the max of it to say that this must have come from this particular device. So just keep it at that. There are a variety of ways in which you can aggregate individual decision outputs, but we take the sum of probabilities. Okay, so let's move on to specific architectures. Now, the vision community has done a lot of work on coming up with architectures that do very well image processing. So our goal was that instead of just starting something afresh, why don't we start from a version which is well used by the vision community? So we started with a version of AlexNet. When AlexNet is shown here, it is a number of about 10 convolutional neural networks, 5 max pooling, 3 dense. So this one is in our experiments still small, because I'm going to show you something much bigger. So this performed very well in some of the experiments that we did. So we call this as the baseline. So if you see that I'm referring to something called as baseline, this is the architecture that I'm referring to. And the other one is called the ResNet. Now the ResNet is the award winner. It always wins some of the competitions that are annually proposed for image processing tasks. Now this is the ResNet on the right-hand side. This is significantly larger, 50 different layers. And the number of parameters that you have to train for this is about 10 times that of the smaller one. So it's really large. It takes a lot of time to train. Now, why ResNet? Because look at this piece. This piece is called as a skip connection. You also see this here. What this means is that the output of a previous layer hops over this intermediate processing blocks and joins back again at a future step forward. So this skip connection is not there in a regular neural network. But because of ResNet has this, the advantage that you get here is that when you train such a network, you're using backpropagation. And when you're using backpropagation, the gradient diminishes as you go from the output back towards the input. And it diminishes at every layer. But because now you have a skip layer, the gradient does not need to go only through this. You can skip over this and the gradient does not diminish. And this allows you to create very deep architectures compared to the regular linear way of creating an architecture, which we have also used. I'll show you some results and which one performs better in which circumstance. But so these are the two architectures that we'll be talking about, baseline and ResNet. Okay, so in the next that follows, I will also tell you some tricks that we have done to identify the signatures. So here is the problem. If you see the IQ samples that are coming in at the receivers, this is this mess. Now, there are two devices here, just two. One is blue and one is red device. But look at the way in which these IQ samples are all mixed together. So how are you going to look at these blue points and say that, hey, this must be coming from so-and-so device? This is all very tightly intermeshed. So there is a trick which we call as partial equalization. Now, this assumes you know what waveform is being transmitted. That means you know that this is going to be Wi-Fi or this is going to be 5G. So in this case, you perform some amount of channel compensation. That means you understand how the wireless channel is distorting the IQ samples, and you propose some level of correction. Now, here is the thought. If you correct too much, then you might be removing the transmitter's signature that it was creating on its side. If you don't correct as much, then the wireless channel will create this mess and you will lose the signature inside it. So it's a tricky piece to detect how much to correct. So we do something called as partial equalization, where we do some bit of correction, but not all of it. So I'll just leave that here. Now, let's start with understanding what worked and what didn't work and what tricks did we use to make it do better. So this is the example where if you see that this is a single example. That means consider that a packet is being sent over the air. You can break the packet into smaller sets of examples, right? A packet is nothing other than a stream of bits. Take the bits, group them together to form one example. So if I take one example, I'm only getting an accuracy of 64% for 100 devices. That means with 64% accuracy, I can say, using these architectures, that this belongs to this example belongs to so-and-so device. But I want to do better. So what if I group these examples together? I say that, hey, if I receive these 5 or these 3 examples back to back, they must belong to the same device, because the wireless, the way in which you reserve the wireless medium, you reserve it to send one complete packet. So if I receive a bunch of these examples from the same device, back to back, I say they must be from the same device. So I can use what we call is a multi-burst technique to say that all these 3 must come from one device. So give me the ID that maximizes the accuracy for all 3 at one time. If I do it that way, then suddenly I see that, hey, I'm at 99%. I can, with 99% accuracy, I can detect a device by simply looking at its received IQ signals. If I use this kind of a multi-set approach. So I say all 3 must come from one device, so this must be that device. So I've shown you here that what combinations work. Sometimes baseline does better, sometimes resonate does better, sometimes we should equalize, sometimes we should keep raw. So this is just an example of 2 waveforms. One is Wi-Fi and one is a waveform called as ADSB. Now, ADSB is used by airplanes to broadcast their location coordinates. It's a very simple waveform. Wi-Fi is a lot more complex, and you'll always see us doing better in Wi-Fi than in ADSB. Okay, so we want to improve the classification accuracy. Why? Because as you saw, with a single example, we were only doing 64%. So I do want to make that better. So to do that, I do something else. I'm going to show you some tricks. So one trick is this. This is the incoming slice. That means a small set of IQ samples, right? And what if I could compensate for the channel in the sense that remove the way the wireless channel is distorting the IQ samples and thereby obtain a clean representation of the signal the way the transmitter actually transmitted it. That means the wireless channel distortions are not there. The transmitter side distortions are there. So what if I could create this kind of a block that can remove the wireless channel, but keep the transmitter side as is? So to do this, either I can use my domain knowledge, and that's what I was doing for the Wi-Fi equalization. I remember I mentioned partial equalization. I was using that domain knowledge. But what if I don't know the waveform? What can I do? So can I create a new kind of a neural network that will simply learn this channel distortion and remove this distortion in the received samples? So we tried that as well. So this is one trick. I'm going to call it as learning the channel. So keep this in mind. I'm going to use this trick when I show you the results in the future. Another trick that we can use is called data augmentation. Now, data augmentation is like this, where you have some data sets, but it is not generalized enough in the sense that you don't have enough samples to train a good network on, or you may have an imbalanced data set. So certain classes have lots of data, but some classes don't have enough data. So you need something called as data augmentation. So what we do in data augmentation is we take in an input slice, that's what we have, but then we distort it at the receiver side through a bunch of different finite impulse response filters. So if you've done a class on communications or signal processing, you will know what FIR filters mean. Simply put, they are distorting the slice that is coming in. So I can change these FIR filters. I can keep rotating them one by one, and I can create distorted versions of this input slice. That means I have somehow my signals have seen a lot more than what they actually have because I've used this method to distort the incoming signal. And I can then train the network on a very large data set composed of these distorted signals. So that is what is data augmentation. So this is just to give you a little bit more details of what exactly is working. So let's just skip some of the minor points and just come to this. So these are the original slices. IQ samples, vectors coming in. All I'm going to do here is that I'm going to take these filter coefficients drawn randomly from a Gaussian distribution, distort them, and then use this distorted version to train the classifier. You just have to keep that high-level idea to understand what this is going to be. So when I'm testing this, now here's the problem. If I'm distorting my training set, I should also distort my testing set in a very similar statistical sense. Otherwise, I might be completely distorting the training set in a way that they are no longer representative of the testing set. So for that reason, whether it be training or testing, we pass them through the same kind of an ensemble filter method and use these for the eventual testing accuracy. So each testing slice is then combined over 10 FIR filters, and then you just you perform your accuracy over 10 versions of the same test slice. So this is simply saying is that distort, distort, distort. That's the takeaway message in the slide. Now, did it work? It worked because look, this is the original multi-bus scenario, but now for the single example case, I have pushed up my accuracy from 64% to 85%, combining the beating the channel approach where the neural network automatically learns this channel and the data augmentation approach where the slice sees a lot more channel variations than it has seen before. So the question now is, you may say, hey, all this time you spoke about identifying a device through its hardware signatures, but you're using a protocol. So what is to say that you did not learn the MAC ID? Because every packet has an ID. What if my neural network learned the ID instead of learning the signatures? Right? That's a fair question to ask. So I'm going to prove this to you using an example of this particular waveform called as the ADSB waveform. Now, the ADSB waveform is a very simple waveform, but just the takeaway message is the first 800 IQ samples have a preamble, and after that starts the data. That means if there is an ID of the packet, it starts from the 800 point mark, 800 IQ sample mark. So in other words, if truly my network was only learning the ID, then I would expect that as soon as I start adding more and more ID in my training set, I will shoot up my per example accuracy. So before this, there is no ID because it's only preamble. ID starts after this 800 mark. Now, so if I see this in my testing accuracy, then I know I have a problem. But what I see is different. I see that in my testing accuracy, the accuracy is relatively flat and plateau-like even before any ID is seen by the classifier. So there is no ID in this space. It can't be learning the ID. And of course, some little bit of slope is expected because you are feeding more and more data into the training. So more data you feed in, the better you get. So some slope is expected, but it is nothing as dramatic as this. So yes, we are not learning the Mac ID. Okay, so you may say that, okay, now you solved the problem, right? You finished the problem, you did, everything is looking good. What is the problem? The problem is that if you train on one day and you test on another day, then again, we are back to low accuracy. And this is because when we created the architecture in the training set, we also learned a little bit of the channel. And when the channel changed, even though we tried to remove the channel to the best we could, we still learned a bit of the channel. And even though the channel changed eventually, it's still affected by testing accuracy. So now I must find a way to beat the channel on different days. So on this side, there are a variety of ways in which you can beat the channel. So I'm just going to tell you very briefly about two ways in which you can do this. One way is, look, what if aside of the inherent signature of the transmitter, we are able to add an external signature. We're able to add something artificial, and that we call as the DC offset or the IQ imbalance. Now, all this means is that you can leave out, you can tune out the comms-centric pieces of it, but the take-away message is you can distort the radio intentionally by introducing offsets and imbalances. And thereby, you are allocating to it a signature which is more robust, which can withstand a different channel. So you're just completely changing its native signature into an artificially injected signature. So this is the scenario, what I'm talking about. And if you do it that way, and this is an example of adding the IQ imbalance. Now, the take-away message is this. If you can do that, if you can add a certain imbalance, let's say imbalance version 1, then whether you transmit symbols over the air or the cable, they're exactly overlapping. Here in this example, if you're adding a certain imbalance called number 2, whether you do it, whether you add those imbalances to radio 1 or a completely different radio, they're exactly the same. That means you are injecting an artificial imbalance, modifying its inherent characteristics, and it is becoming someone else. It is becoming a whole new radio, but this new radio, you can detect very reliably on different days, on different channels, and it's completely in your hand right now. And indeed, so you see that in some of the experimental results that we did, this is when we train and test over the cable. You train and test in a certain location, in the same location. But here is the problem. If you were not doing this without the impairments, this would be a bad confusion matrix that the 16 radios would be confused with each other. So this adding these impairments are making it completely impervious to the wireless channel. I'm training it over cable collected data, and I'm testing this in 2 completely different locations, completely different channels, and no problem at all, 100% accuracy. So that is how you can achieve this. Now, what we have done is we have done something crazier. We have said, okay, we could do it in a room. Can we do it on UAVs? So I'm going to mount these software-defined radios on the UAVs. I'm going to fly them, and I'm going to try and detect these individual UAVs in a very harsh hovering environment and detect which UAV is the one that I have learned that I can detect. I can classify using their IQ samples. So here is the results again. You can see that without adding these impairments, these UAVs, you can hardly detect them. So this only I think we had a 7 UAV test. We could only do about 35%. But now with the impairments, we are at about 100% accuracy also at many different distances. So this technique works also for very different kinds of systems. So one other outdoor experiment that we did was we said, let's take all this into outdoors, into a real large-scale network. So this is a large-scale experimental platform called as Powder. It's part of the Power family of experimental platforms. Now, what they have is these base stations. They have these base stations that are separated by over kilometers length. And here I have a passive listener. So my goal is to detect that this base station is really who it is claiming to be. And this base station can change its waveforms from LTE, Wi-Fi, and 5G NR. So irrespective of the waveform, I should be able to say that you are truly that device or that base station that I know that I've trained over. So changing the waveform should not operate your hardware identity. So that's again, so when we try to do that, it's the same problem. When we train and test on the same day, perfect. We train and test on different days, we see a problem. Now, to do this, now we could not go ahead and change the base station itself, because in the previous case, we were injecting impairments. But in a network operator sense, you can go and tell the network operator, go inject this distortion. You can do that. So you have to do something at your end. So I'll just give a high-level view of this and leave it at this in the interest of time. But what we do is we call is a technique called as the Siamese network with triplet loss. Now, the method works like this. And you don't have to follow this math out here. You can just get a high-level idea of the way I'm going to present this. When you are going to train the network, take the anchor example, the one that you are presently training on. Take one that you know belongs to the same class. So that is going to be from the same device. That's the positive example. And take one from that belongs to a different class. That is going to be the negative example. Okay. Now, pass all these three through the same classifier. Okay. And take these embeddings that are just before the final fully connected layer. Because the neural network is capturing all this information in some kind of an abstract space, right? I don't know what this means. It's hard for me to visualize this, but it is capturing these in an abstract space. So capture these abstractions, which we call as embeddings, and identify how far you are from the positive example, because you want to minimize this, and you want to maximize this between the positive and the anchor and the negative example. So when you take this, when you create a loss function that captures both the positives and negatives, you can retrain your network and overcome this problem. So with that part, I'll just go to the result on this, and you can indeed, through these triplet loss methods, even when you train and test on different days, you are getting a pretty good accuracy, overall 93%. So, and this is how it looks like. By the way in which we were creating these triplet loss methods, you can cleanly separate these 4 base stations in the TSNE representations compared to this real mess that was before. This was before the triplet loss using a normal baseline classifier. This is after the triplet loss, where you can now more separate them in a 2-dimensional space. So this is just a representation of a high dimensional space in a 2D representation through the TSNE plots. So just to conclude, I want to say this, that RF fingerprinting can detect an individual device from a large pool of devices. It's successful in a broad variety of tasks, and we are only scratching the surface as to all that we can do with it. But there are some open challenges. The challenges are, how do you beat the channel? How do you beat the channel with and without hardware-based changes? Can you do some kind of a transfer learning, where you learn these in one channel environment, and you can transfer or learn some new characteristics in a deployment environment? And what kind of automated tools can we create in terms of estimation, data augmentation, etc.? So it's a very rich and open area, and I will just stop here, and I'm open to taking some questions. So thank you very much.
Okay, Kaushik, it was really perfect. So I was listening to it as if it was my first time to listen all this RF fingerprinting and everything that you are doing is really nice. Actually, we have several questions from the chat. Before I start reading them, there is a question of mine. If you don't mind, I just wonder one thing. So as you know, as you are also an expert in this latency and networking area, so in our general delay definition, we had several like propagation delay, queuing delay, etc. So what do you think about the latency process and this AI issue. So is it directly related with the edge computing? So are we going to put the brain to the edge in order to decrease the latency?
Right.
For example, in this RF fingerprinting or in this Wi-Fi distortion optimization and everything.
Right. So you ask a very good question, and this is something that is part of another project called as real-time machine learning. So you will have to invite me again for a talk on that. But my short answer is this: that latency is the most important thing in a communication system. So for the training side, we can't do much. The training will still need to happen in complex GPUs. But for the testing side, we can do a lot. So for example, we have a paper last year where we showed that you can do modulation classification. You can train all of them on a GPU, but for the testing case, you can create TensorFlow-like representations and inject them into an Android smartphone. And then that can be live. That can happen. That's in fact much faster than a GPU when it comes to the testing phase. So there can be smartphone representations of the same architecture for some examples like this. Now, the other thing that you asked a good question on edge versus say cloud. There is a large body of work that we are doing on pruning architectures. This is called as quantization and pruning architectures, where you take a big architecture and you squeeze it down to a point where you can represent it using perhaps just fixed point numbers.
Exactly.
And if you can do that, then you can implement in FPGAs very easily. You can do it on the front end, but it needs a whole different area. So I would say open research will be a great challenge.
Okay, yes. So let me read some question here. So what are the thoughts on quantum communication systems? There's a question from one of our professors. Maybe you can give some big picture about it, because it's a huge array in 6G, and I know you have some personal things in this quantum communication. What are your thoughts about this?
So I have to find my quantum computing book. It is lying somewhere in my study here. I
remember we have taken together that course at the time back. Anyway.
Right. So no, I started to revisit that book, but then it was late in the night probably, and my 2-year-old had given me a hard day, so I gave it up that night. No, but here's my thought on this. Some of the process. So if you need near instantaneous decision making, and especially training in situ, in live, then our current computational capabilities aren't going to work. We will need a very nonlinear kind of a system that can crunch massive number of, in this case, in quantum case, qubits in units of time. Okay. So in my mind, if you are going to do training live and you need instantaneous capability, then perhaps there's no other option. You might have to go that route.
Maybe it's related with the real-time thing that you are mentioning.
It's like this. Think of the matrix. You are here in the matrix. You are injecting something inside, and suddenly you say, "Yes, I know how to fly a helicopter." Right? That if you need that kind of a learning, that pace, then you need something like a quantum computer, perhaps, to crunch numbers at that rate. So all our training is done offline at this moment.
Yeah. Okay. So another interesting question from one of our professors: how to use decentralized network structure, which is operational, for central data flow, or vice versa, central network to decentralized structure. I mean, how this relevant or important in terms of distributed design?
Right. So one of the things that we are actively looking forward is federated learning, where each smaller device is essentially learning an architecture and only sharing weights with the central cloud. Now, why are we doing this? One example that we have for this is, again, for UAV classification, where each, let's say, airport is learning an architecture of all the UAVs that it can data collect for at that location, create the architecture, and then send only the trained weights to the central cloud for rapid aggregation.
Yeah.
So this has a lot of promise. It's also used in smartphones a lot for identifying the typing characteristics or other handwriting recognition of persons. So federated learning is going to become very big in the days to come, especially driven by privacy constraints. So in my mind, distributed learning is a very active and open area, but the tools that I know that we use as of today is federated learning. And if someone wants to start work on that, there is a lot of good literature that can bootstrap research efforts on this in this domain.
Exactly. It's like a chicken egg, like the decentralized and the central network and centralized in the decentralized network. Exactly.
Right.
Another question, a nice one. Are the numbers of classes scalable, or is it a classification problem with a fixed number of classes, like a binary classification?
Right. So in all that I showed you today, it is all fixed number of classes. But there is, again, a new work that we have just submitted. It's called as lifelong learning in collaboration with some of my faculty colleagues at Northeastern, who are also machine learning experts. In lifelong learning, what you do is you identify that you have not seen a device of this class before, and you add on that class into your set of classes of the neural network.
Oh,
so the way you do this is that you still need to modify your architecture a little bit. In this case, that you freeze a certain layer and you add additional layers over time. So there's a method to that. But broadly, lifelong learning is, again, an active area of research. And what we do here is that we show the architecture, the process, 20 devices, and then we show another 5 devices at testing time. Mm-hmm. First is to identify that this is an out-of-library set. That means you have not seen it before. So that's the number one step. Then the next step is to create classes of these unseen devices. So yes, this is a paper that is just submitted. So, but this is something that we have looked at, but though not covered in this talk that I presented.
Yeah. Okay. Another question. I think this question has 2 aspects, as the person writes. I am curious about 2 aspects, mobility and latency. The first part is there should be new signature around the medium in real life applications. How do you have any method to mitigate this type of new signatures if you are talking about mobility? And in the second part about the latency, do you expect to have FPGA like hardware to address this CNN process? If you want, you can just combine this to your answer.
Yes.
With the...
Right. No, but these are important questions. So here's my thought on this. When you say new signatures, I look at new signatures in 2 different ways. One is a signature distortion because of the wireless channel. And that is distorting a signature and thereby creating a new signature which your trained classifier cannot detect. Yeah. So to do that, we spent a large part of the talk trying to counter that using different kinds of injecting impairments, triplet loss, and such other tricks that we have. You can also do data augmentation by training the set over multiple channel realizations in the new environment that the device is likely to be in. For example, you can train it over distortion that might be relevant for a Rayleigh or a Rishian trading channel. So you can do that before you've gone to that area. But these are all channel distortion signatures. The other thing is new signatures in the sense that a new device that you have not trained over is in the area. Mm-hmm. And for that, we have a paper last year in DICE-PAN. I did not cover it here, where we basically call it as outlier detection. Mm-hmm. And the method is very simple. We simply say that in the training set, for each device, we saw a certain number of accurately versus inaccurately detected slices for every correct decision. We just take the same statistics and we see that now you show me a new device, say device number X that I have not seen before. Remember that when I'm doing my classification accuracy, I'm breaking this into slices, small bits. So if the statistical representation of the accuracy in those small bits doesn't reflect what I have seen in the training set for the predicted class, I say that this is an out-of-library device. Because at the end, there is the output will always be a probability vector. So it will always map any unseen signal to one of the previous devices. That's what the neural network will do. But I will then go back and check statistically, does it make sense from the number of slices that say it is the same class from the number of slices that I've carved out from the example.
Okay.
So we do that to do outlier detection. So yes, unseen signatures can happen is in case of outliers, but also then there's a question of lifelong learning. If I see this multiple times, maybe I can create a new class in itself and recognize it next time I see it. So that's the part that connects to the previous question.
Okay, so just to finish that question about the FPGA for the CNN process.
Yes.
Do you expect to have FPGA like hardware to address the CNN? If so, the question, this should create power-hungry solution. Do you see any potential for research to work on low power solution to run CNNs? I think it's
absolutely. So, for example, FPGA is only one side of the bargain. So there are various ways to do this. So I can point you to our DICE-PAN paper last year where we showed modulation classification running on Android phones. Basically, it takes the architecture, it passes through the TensorFlow Lite converter, and it's very magical. It just compresses the model, amazingly small, and makes it very efficient. We show that it can reduce energy consumption by order, 10x the amount.
Wow.
When you're running it, that compressed model on the smartphone.
Originally, they are so power hungry, right? So originally, before all these things, they were so power hungry. I mean, lots of energy consumption were happening before that.
So before that, you're thinking of like watts of power, several watts, and now and right now it's going to be some milliwatts. So about 3 orders of magnitude smaller. Okay. And also for FPGAs, just keep in mind that you can do efficient FPGA implementations. You can convert them through pruning and quantization into formats which can be represented by only few number of bits. So we can reduce, for example, ResNet down to only 4 bits of representation. With only 4 bits are enough for you to represent all the weights of the millions of weights that are part of a ResNet architecture. So that's another work that we've been doing.
Yeah, lots of new vision that the questions are coming, Kaushik. As you see, as you speak, there are several questions from several sides. One interesting question from IRL base stations. Remember this IRL flying base station?
Yes.
What do you think about the effects of AI implemented on IRL base stations?
Well, is there a way out?
Big question.
Look, I think so. The fantastic vision of Skynet is not too far away, where you have intelligent UAVs making independent decisions. Now, I only showed you here the fingerprinting problems, but we have also worked on many other problems of, for example, can the UAV use its cameras to detect its environment around and take other logistical actions like moving in a certain directions by recognizing locally what it is seeing around and creating a mesh. We have also looked at creating fine beams. For example, look at millimeter wave systems that need very fine-grained beams across the receive and the transmit point. Now, if you do this through the regular wireless protocol method, it is going to take milliseconds. But if you use cameras, you know exactly, you can learn how far you are in distortion, in relative position you are from each other. 2 UAVs are from each other, and slowly they can adjust and come in full alignment. So many ways it's going to happen. The only thing is this: we use the NVIDIA TX2 board, which is a compact AI engine that we have mounted on the UAVs. So if I can go back, maybe I can show you this. The UAV board that we have here. So this is the TX2, that is the Jetson TX2 that is sitting on the UAV. You have to be careful about size, weight, and cost and power, or we call them as swap-C constraints. So you can't really have a big GPU sitting on this one. So it has to be something lightweight. That is going to decide how much you can do on site and how much should you stream down.
Yeah, exactly. Okay, another question. I mean, I continue to the questions, Kaushik, for maybe 5-10 minutes.
I have all the time. Please go ahead.
Yes, I know you. So another one. Since 6G is not currently used, how can we overcome the challenge to access 6G data to analyze and to find somehow solutions? So how can we process the non-officially existing 6G data? So maybe like.
Right. Right. So here's my take on where does 5G end and 6G start, right? So 5G allows a highly decentralized mode of operation, and it allows hooks into where some learning can happen. But 5G, at least to my knowledge, does not have a machine learning framework that is built into its complete communication systems choices. For example, the system is not fully AI driven. So in my mind, the transition to 6G will happen there. Once the 5G creates the underlying fundamentals of the infrastructure, the technology, the mature the knobs that you can tune, the open source access that you need, then comes the whole machine learning community should come in and start to develop these intelligent methods. So it's not going to be completely, in my mind, a completely different, you just throw out all you have and here comes something completely new.
Yeah.
But you're going to have a fully softwareized intelligent plane that is going to sit above this entire ecosystem of hardware.
Exactly. The Wi-Fi 6, for example, has this kind of software plane, right? The new Wi-Fi.
Right. Correct. Exactly. So in my mind, we should not be waiting for 6G protocol standardization. We should be building enhanced real-time AI ML engines that will fully automate and make 5G networks supremely autonomous and intelligent. And that is a smaller, or a let's say an easier fruit to have in a near term.
Yeah. Another question, does this relatively long convergence time of machine learning weaken the usefulness of ultra-dynamic wireless networks? So since we have like a long convergence time in machine learning algorithms, does it have any effect on the usefulness of ultra-dynamic wireless networks like aeronautical networks? So we are changing dynamics too much.
Right. So I just for me to understand better on this one, right? When you say convergence, is it the training convergence? So, for example, ResNet, some of the examples I showed you would take about 7 days for it to be trained. So each result is over 7 days of continuous GPU cycles on a V100 NVIDIA GPU. So it takes time to converge. There's no way around it. But here's what we can do. Google and the likes of these companies have trained these large architectures using as much power as it would need to run a small village. Okay, so they have put that much resource into it already. Let's take those. Let's strip away the last few layers and freeze some of the previous layers where some of the, let's say, underlying features are being learned. And then let's start to tune these in a way where, to call it as an advanced transfer learning, where we can speed up the convergence time significantly. Now, we have to be careful that not every image trained classifier will work for an RF scenario. So what will work best if you take an RF trained classifier for, let's say, IQ sample pattern detection, and you just freeze the first N layers and then just tune the last few to just adapt it to your application. That will speed up convergence.
Yeah.
But other than that, unless the other gentleman who said quantum computing, it's going to be hard to do this, to magically make that disappear. Now, but that is the training convergence. The inference must still be very fast. So we can still do fast inference today. So once it is trained, we have methods to reduce it, quantize it, make it small, make it efficient, so that you can have very fast output decisions. So that we can do. So that should not be a problem. The training is generally a problem.
Yeah. Okay. Another interesting question. Let me summarize the questions. Since I am also working in the SDN. So the question is related with knowledge-defined networking, KDN. So it says, what is the relation with 6G and AI-based SDN that is newly called knowledge-defined networking?
So there's a thought here that we will no longer have, standard regular packets defined by the whole IP. The whole vision of IP will go away. Yeah. And it'll only be everything will be data centric. So data will define which paths you take, how do you go forward, and so on. So we are not there yet because we are still in a very IP world, and I think we will remain in an IP world for the next 10 years or so. That's my projection. Now, when you start to look at knowledge-based networking, though I take a pause because I am afraid there is a machine that is doing some kind of a deep packet inspection, understanding the context of the packet,
exactly,
understanding what I'm trying to say, and then making some kind of a routing decision or some kind of a control decision based on that. Am I willing to give up? Is anyone willing to give up that level of privacy?
This is another big topic, like the security and privacy.
It's a big topic. Yes, indeed. So I don't think we are ready to relinquish that control to machines yet. Mm-hmm. But until we are mentally ready for that, I don't think it's a technology problem. I think we can come up with good contextual inferences from plain text, right? So there are a lot of programs that do that. They do automatic translation. They do some kind of a context, capturing context from sentences. But it's more a human problem as to are we willing to give up that last bit of privacy for perhaps a more optimized network? I'm not for now.
Okay, let me summarize the question. So do you have a comment on solving complex path planning problems for autonomous drone networks? So the path planning that we have, actually, it's really an AI-driven, maybe there are some AI-driven approaches for this. Like it can be an NP-hard problem, as the question also says, but with AI, maybe with some AI algorithms, it can be solvable, right? I don't know, not the NP-hard, but the path planning.
Right. So in all of this, I asked myself that what is going to be the data set and what is going to be the output class, right? So for example, if the input feature is, let's say video cameras or images or audio that the drone is collecting live in the field, and the output becomes where I go left, right, or center. So if we can reduce any such problem into this kind of a clear input-output problem, I think there's a lot of scope for that. But the problem in a general routing problem is creating a data set that is rich enough. For example, you can't really fly a drone at every location and capture all the possible visuals that it can ever see. So you don't have that kind of a data set to train it on. So how would you then create that data set to do this path planning problem? So remember, the machine learning thing you should only use as a tool of last resort. Okay, this is not something. So if you can do something in a deterministic manner, go ahead, do it in a deterministic manner. If you can give performance guarantees through an algorithmic approach and a theorem, go ahead and do it.
Yeah.
This approach, I'll give you the example because as you can see here, the only reason why we did this kind of a deep learning approach was that there was no way for me to know what would be these patterns, and especially once these patterns are all superposed together because of these multiple different electronic components. I cannot learn this. I do not have a deterministic version for this. So I had to do deep learning. So if there is a version of the path planning problem, so just because it is NP hard doesn't mean that you can't have efficient approximations for that.
Yeah.
Right? So that's where I want to find a nice balance.
Yeah. Another question is that I think ResNet has lower number of parameters as compared to AlexNet. Why you didn't try the CNNs with lower number of layers?
No, in fact, ResNet has probably 10 times the number of parameters compared to AlexNet. It's huge. In fact, if you just see this, I don't have the exact number of parameters, but it is at least 10 times over AlexNet. So it's a much deeper architecture, much more parameters. It takes, and each such iteration, it's an epoch takes us days on ResNet compared to minutes on AlexNet.
Yeah.
Now we tried simpler architectures, and so, but they were not as effective. They were not able to capture the the latent representations as well as deeper architectures at the end. So for every result that I'm showing you, there are at least 20 things that we tried that didn't work. Mm-hmm. And it's for us, it's been a path of trial and errors in some ways as we started to look at different architectures and grow in size. But one thing we wanted to do was use something that was existing and modify it as compared to design one from scratch. Yeah. So that's, but I can assure you that we did try the smaller ones. They were just not as effective for this problem.
Okay. So some more, not questions, but they are asking your opinions. You know, our students are really curious about your opinions after such a visionary presentation. So one thing is that I would like to learn your thoughts on how we can implement lightweight training models to capture drastic changes in this physical environment. How we can implement.
So if I knew that secret, I would probably be making a company and be earning billions myself. So the short answer is
that doesn't exist right now. I mean, this dynamic changes in the physical environment is really a huge challenge in our world. I know this. So
right. So I can only suggest some tips on this instead of the solution. But and if you solve it and you become famous, remember me. So one trick is that try transfer learning, where you are freezing a good number of layers and training only the last few layers. Try pruning and quantization to reduce the scale of the architecture. The problem that happens is that the training process is expensive, but the inference time is much faster. But if you want to adapt it live in a lightweight manner, there's very little that you can do in an in situ training method. So you have to train it in a small device, which is not, which was never designed to be that parallel. So we make use of the parallelization in a GPU to get speed ups. A small device is not going to have that level of parallelism. So we can try transfer learning. We can try some kind of learning with a fixed point representation, but those are obviously going to affect your accuracy at some point.
Okay, so there is another big type of question. I will leave it to the end. Like, what are the challenges of 6G when we consider the effects of AI? So let's have it to the last as your last wording, because it's a big question to answer. Another question. So what do you think of usage of the machine learning and AI for UAVs in mission critical scenarios? So
correct.
You can give some.
So here's a thought here. So we have recently started a lot of work on multimodal AI or multimodal data learning. So what we are trying to do is that when you talk about this mission critical UAV applications, the way I interpret this is that you are going to get a large number of different feeds of different data types. They could be telemetry. Yeah. They could be video, audio, and images. Okay. So when you have all these modalities, you need to somehow construct architectures that can digest these different kinds of completely different modalities of features and parse a common answer. So the goal is to focus on multimodal learning and multimodal data sets and develop those pipelines. Go beyond vision, go beyond RF, start to combine them together.
Exactly.
And that will really save the day for these mission critical UAV systems. And that's what we've just started to work on as well.
Yeah. Actually, the rest part of the question was directly related with the multimodal. So how can we cope with the risk of adversarial machine learning during the raw data transmission? You answered the question before knowing the question. So direct.
So, but you ask a good question here. So you ask a question about adversarial learning. So adversarial learning is a whole area in itself. Now, we had a paper last year where we were saying that, you can communicate information by, so let's say I showed you some methods where we could do some distortions of the IQ signals and so on. So you can also do this intentionally and communicate information to someone else without any third party knowing that you are transmitting this. because you are distorting the signals, and a machine learning classifier can identify those distortions. So you can transmit 1-0 bits and combinations, and you can detect those things. So to relay information using machine learning is a very open area, and there's a lot of good work to be done. But the adversarial action is interesting because now the adversary can try and spoof your signatures, your system. So perennially you will be dodging them. So they will try to learn, they'll capture your IQ samples and try to become your signature, and you will be then over time dodging them, sort of moving away from a previous signature that you might have exhibited. Yeah. Right. So it's a question of, again, using the triplet loss method. If you go back here, remember we are looking at a positive and a negative example. So the positive example could be here. So I was showing you one example as anchor, same device, different device. So in a way, if you show yourself, if you show your own example as negative in a future time, you can start to create a new network that actually embeds or injects signatures that go away from your previous signature. And you can do that over time. So we call it as impairment shift keying, where it's shifting your impairments like a Bluetooth signal is hopping over time.
Yes. Okay. So about the previous ResNet question, so that I think there's another comment. AlexNet has 62 million parameters, and ResNet 152 has 60.3 parameters. There are only 23 million of parameters in ResNet 50. AlexNet has not more. I mean, just the comments. I'm just reading the comments to you. Maybe you can have some additional comments after this. The ResNet has lower number of parameters because it has only one fully connected layer at the end, and AlexNet has 3 fully connected layers. So maybe it's a question of this layered architecture of these 2 different structure, right?
Yeah. But so is the comment that you can train ResNet faster than AlexNet?
Yeah.
Well, we didn't certainly see that in our.
There are just some comments related to the previous answer of yours, probably, and maybe he or she wanted to make some more comments on this. So for the last one, what do you think about the challenges of 6G when you consider all these artificial intelligence effects? So maybe you can give a short 2-3 umbrella answers that we are to hear, so we can start to close our session.
So here's my thought, right? 5G is going to create a rich source of knobs, levers, hardwares, and systems, and open source tools through which any of us will be able to turn knobs. 6G will bring in that layer of extreme intelligence, in my opinion. Now, to solve the problem of 6G, to give that much control to the machines, we will need 3 things. We will need some kind of explainable AI, where we are able to reason as to, in a way, that this will always work, or this is how the process is working. Yeah. We need to be able to understand this better. So we need that step. First, we have to do this in the next 10 years. Yeah. Then the next part is some kind of a guarantee that it will work in regions and locations which you have not trained on. Now, think of it this way. When you have, at least in the US, when you create a new device, you have what we call as an FCC certification process, where this device is tested by the agency, and it makes sure that your emissions and spectrum use and all that is within limits. Yeah. So what happens then in such an agile environment where you can adapt and change your characteristic, your signature, your emissions over time? How do you even certify a device like this? So that is unknown. So we have to solve a problem of also policing and certification before we start to even deploy them. The third thing is real time. Real time is key. So far, we are only scratching the surface because we are using data sets which are collected, saved, stored offline manner with some small tuning that we can do live. Yeah. But the 6G, we will have to do all of this process in real time. So we'll need a completely different paradigm of computing to do this in real time. So these are my challenges. One is, one is, as I said, explaining the system, like being able to explain and predict AI behavior. Second is ways to police and certify AI capable devices. And the third thing is what we just discussed. So all these three things have to come together.
Yeah. Just one last question. How effective is RF fingerprinting against frequency agile methods like frequency hopping, etc.?
So to do this, look, we wanted to stress test this system. So in a sense that when I showed you these results on this topic here, we used three different kinds of waveforms. So we used Wi-Fi, LTE, and 5G NR. We combined all these signals together in one big jumble.
Yeah.
And we tested as if it was all a mixed set on different days, right? So think of this, they're completely different protocols. And still, we were able to get this kind of an accuracy. But this is not a frequency agile in a sense. It's not frequency hopping. But if we can detect in the same frequency, from IQ samples in the same channel, we can make these kinds of learnings and inferences. We can also add on the hopping pattern as another layer of knowledge to be learned.
Yeah.
I can perhaps learn your hopping. I can only add on. I'll make one more column. I'll say hopping characteristics. So, but this should be independent of really the agility of the frequency.
Okay. Yeah, Kaushik, we had really so many questions, and they were all asking your valuable comments. So we don't have any more questions. Before closing this really precious session, I'm just wondering, do you have any suggestion for the newbie students who want to deal with AI and smart networks? What they should do? They should, in terms of courses, in terms of disciplines. What do you have any suggestions as a really well-established academician in this area?
Am I well-established? Well, I'll just say this: that look, this whole area is new to me as well, and in the sense that it was just a couple of years that I really took a textbook and started to learn this myself. So, bottom line is that if I can do it, you guys are way smarter than me. You guys can pick up really fast. So you're in a good point in time to be in. And this is probably the best time to be in this area at this moment. Data is easily available. Computing is easily available. Knowledge is online and through books and through lectures. This is the best time that you should not let go of this. You should utilize this. Yeah. And I would just say that think big and think crazy. And even if not everything happens, you might just find a new spark somewhere and make the next $1 billion. And then again, as I always say, think of me.
Yes. Dear Professor Chowdhury, it was a fantastic presentation and fantastic webinar with you. I really want to thank you very much for this opportunity that you give us. If you don't have any comments, we don't have any questions, so we can close our session. Do you have any?
Very much. I just want to say thank you very much. I'm always very honored to be a guest at ITU. I've come once before, and whenever again that you need my inputs, I'll be very eager and willing.
Always. Your inputs are always valuable. Thank you very much, Professor Chowdhury. We are closing our session. Goodbye.
Bye-bye.